Before I come to the official definition of a monad, I want to just repeat what we've done in previous lectures in case you jump directly here. So, quick recap. First, we just looked at monoids. So, what was a monoid? So, a monoid is an algebraic structure with a set, say M, and certain operations, say E, and I write a dot for a binary operation, which could be concatenation or multiplication or addition, just a binary operation. And then we also have equations. So they are expressed in variables. So if x is a variable, then we have an equation which is saying that E acts as the neutral element for multiplication, and also the other way around. And then, most importantly, there is the law of associativity. So in our story, the monoids here at that point are just an example of a structure that is defined by operations and equations. Okay, so the second thing we looked at was the free monoid. So among all the monoids, there are free monoids, and they will be important to us in the following. So let me just review this. So we wrote this down in a more mathematical notation. So if you have a set X, then we can form the set of all finite lists or finite words over X. And the common notation for this is the star notation, Kleene star, x to the star. So this is just the set of all words over x. But this is also, as it happens to be the case, the free monoid over x. So what's the monoid structure here? The empty word is the neutral element, and concatenation of lists is multiplication. And the elements of X we call variables, because they play the same role, they play the role of variables up here, right? But also we call them letters if we think of the elements of the free monoids as words. Okay, and then we also gave a more programming-like notation. So this is pseudo Haskell if you want. So then we can define the free monoid over X as the set of lists over X. And in Haskell, we could, for example, say the empty list is called nil, and the list is either empty or we append an element of X to a list. So prefixing is maybe a better way of calling this operation. So we take a list and we prefix it with an element from X. Okay, so free monoids. And then we also said free monoids have a certain structure. And I will repeat what this structure is because this is exactly what will make up the definition of a monad. So we will have two operations called eta and mu traditionally. And so in the case of lists, what is the eta doing? It just takes a variable and turns it into a list that contains the X. So a singleton list. If you think of X as variables, then this operation is also called insertion of variables. And if we write the same operation kind of more in Haskell style, in programming style, then I would define it as eta X is the list that just contains X, so it's cons X nil. So that would be writing that down the same definition in pseudo Haskell. Okay, and then there's another operation which is called mu, and it is takes a list of lists and turns it into a list. It's also sometimes called flattening. And it can be defined like, let me define it in a programming style notation. So if I flatten the empty list, I get the empty list. And if I flatten a list that is not empty, so a list which consists of an element and another list, then I take the first list and let me use this dot notation for concatenation of lists. So we have said already that this is the free monoid, so there must be a multiplication, and we denoted, we used the dot for multiplication before. So let me use it here again. And then what I need to do is I need to flatten the tail of the list. So maybe for notation, I write axis here because the head of this list is a list, and I write XSS here because it's a list of lists. So the number of S's is just there to indicate the type if you want, right? So a list of X's and a list of X's. Okay, and then we also looked at the equations, which I will not repeat because we will see them in a moment when we look at the official definition of a monad, but there are equations for eta and mu. So all of this does not require understanding the idea of a monad at all. It's just particular structure which we extracted from the particular example of the list monad or the free monoid monad. Okay, so that was the important example of free monoids. So next, there's another another section, another idea we should know before we go to the general definition of a monad, and this is the notion, the general notion of an algebra. So here, the step is we generalize from the particular example of a monoid to the more general notion of an algebra. So we generalize, and the idea is simply that a monoid, we have seen, has a neutral element and a multiplication, and so these are examples of operations. And then we also have seen that there are various equations like x times e equals x and so on, so equations. So the idea is just that we now generalize from a particular algebraic structure such as monoids to a general algebraic structure, and a general algebraic structure is just defined by a collection of operations and equations. And now there's an obvious question, which is, how do we generalize the free monoid construction? Right, so we have seen the free monoid over X. That was item 2. And if we generalize monoids to algebras, obviously we should also generalize the free monoid over X to the free algebra over X. And there are two ways of doing this. And the first one is kind of concrete. It's called the term algebra. And the term algebra, we have seen, is built from operations and equations. So we take the term algebra over X, I should say, right? So the term algebra over X is given with respect to a particular set of operations and equations. So what we do is we just form all terms, which we can build from X, from the variables, as our kind of basic building blocks, and from X and the operations. And then equality of terms is given by the equations. So that I should also say that we have a notion of equality with equality on terms given by equations. So that's one way of generalizing the idea of a free algebra. And there's another way, and that's exactly what leads us to the heart of the matter, namely to the definition of a monad. So instead of being concrete and define a free algebra in terms of the particular operations and equations, there's also a generic way, an axiomatic way of describing the free algebra over X, namely by axiomatizing the properties of eta and mu. So what I'm saying is that a free algebra axiomatically is a mathematical structure that has eta and mu satisfying certain equations. So this is the other idea, axiomatizing the properties of eta and mu. Okay, so to summarize, I'll shortly see the definition of a monad in all detail, but what it will be about is a functor M on a category C with two natural transformations, eta and mu, satisfying certain equations. So M will be a functor on a category. Eta will be a natural transformation, and mu will also be a natural transformation of the indicated types. So before we conclude, just one remark on notation, which will come in useful. If you want to read the definition of a monad, so I give you a remark on notation, which is hopefully helpful. So I want to explain just a little bit more what this ID here means. And so really, let me just scroll quickly back here. Maybe you've spotted this. Oh no, you didn't spot it because I didn't put this notation in. So in mathematics, if you have a natural transformation, which is parameterized by choosing an object X in the category, you usually put the object here as a subscript, right? And actually we don't do the same if we write down the programming notation. So in Haskell, for example, you wouldn't put subscripts here, but in mathematics you put subscripts. And when we drop the subscripts in mathematics, we really denote the natural transformation. We put the subscript, we look at the particular error at a particular object. So if you have a natural transformation from ID to M, then ID stands for the identity functor on the category C. So every category has an identity functor. And you see now how it works. So if I want to instantiate this natural transformation at a particular object X of C, then what do? I apply the two functors to the object. And now you see that because the identity of X is X, we get the correct type which we wanted to have for the natural transformation eta. So the identity, to use the identity functor here is just a way to match the types in the correct way. So now, what's next? So actually I will not make a video where I write down the definition of a monad, so I think you can best read this for yourself. So Next is read the definition of a monad. For example, in my lecture notes or on Wikipedia or on some other source, and then do the exercise. So we reviewed the free monad, the list monad. We even called it a monad, even though we didn't have the official definition yet. So as an exercise, verify that list is a monad. I will actually do a video on this, but I think it's best to do this first on your own. Thanks for watching.